Okay, let's get started. So hopefully I'm going to be able to record the derivations on my laptop, so that's the plan. Last time, I don't know if any of you checked Panopto, but essentially what happens is it records the PowerPoint presentation as it changes. So if you looked, what you would have found is the video, the actual things that are written on the slides don't update. So if you look under the course on Blackboard, I've just reorganised this. So we have everything from Lecture 1 under the folder Lecture 1. Right. So there's essentially a video here of the slides and audio from the first video. And then what I've done is I've re-recorded just part of this, where the derivation of the interpolation function. So this actually has basically all of the details of how we derive these interpolation functions. What I'll do is I'll cover everything else again today that's important, but hopefully combined with that video that shows you how to do that kind of key bit of the derivation, you've also got the lecture notes here, which are basically step by step how you actually go through and work through those various bits. So I'm not sure if anyone had a chance to look at this, but this is the first step in the mathematics we're going to cover in this course. So it's well worth just going through and making sure you understand this. And there's an opportunity for me to cover this again today, depending on whether you think we need to. And then there's also the lecture slides on here that are annotated, so the end result of our last lecture with all annotations. So everything is on Blackboard. Any problems accessing that, please let me know. Were there any questions since last week? We had time to, or 2 weeks actually, sorry. Anything pressing? Okay, perfect. So let me try and project from my laptop. And I had some problem with this before, which is why I've got this open, because it seemed to struggle to keep up. But we'll see. I mean, let's give this a go. This is kind of an experiment. Hopefully it records correctly. Any problems, I can re-record the key bits. Okay, perfect. Good afternoon. So today, the plan really is we're going to go through basic introduction. We're going to talk a bit about the survey from last time that hopefully most of you have filled in. I'll put the link up again, so please, if you haven't done this already or you want to update bits and pieces, please do that, because the more you feedback to me, the more I can kind of tailor content. And even if this is as simple as you saying, look, no idea what you're talking about, please slow down, please cover this again. Just take the time to fill that in, and I'll try and take that into account in the lectures. I'm going to go for a recap of last lecture. It's been 2 weeks, so I assume most of you have forgotten everything we talked about, so I'll at least go through and cover the key bit of the derivation. And that is essentially the interpolation functions. You've now got the videos online. And then we're going to move on and talk about an example solution to a one-dimensional differential equation. So it's not particularly exciting, at least at first glance, but I'll try to explain to you why this is essentially an equation that models lots and lots of physical phenomena. And one of the things about this course really is that the idea is we cover as much detail as possible the fundamental methodology of finite elements. So we're really trying to get into understanding exactly what happens in terms of boundary conditions, in terms of numerical solutions, in terms of approximating solutions. And then it's just simply a case of scaling up to more complicated equations. And I'll talk about the more complicated equations, but the idea, as I said before, is to get the kind of fundamentals in place during this course. Depending on time, I'll then finish with a kind of more expanded version of what I hinted at last time. This is the kind of link between what's called the weighted residual method, which is how we get these finite element forms of the equations, and the more general idea of how we actually go about approximating and solving equations in physics and engineering. And I'll keep coming back to this because the idea really is to highlight to you what we're trying to do here and why this works as a methodology. Okay, so we're now on lecture 2. This is week 3. We didn't have anything last week. And then just a reminder, we're going to be having, for the next 2 weeks at 2 o'clock, same lecture theatre, and then just by week 6 we'll have a lab, but I'll remind you about that. Okay, so just coming back to the survey, there's the link there if you want to fill it in if you haven't done that already. It's also on the Blackboard site. So again, if you haven't done that, please do. The idea really was to try and get a feel for your different backgrounds, and then also an opportunity for you to sort of essentially say what you want to get from the course. So please feel free to add to that. We've also got this QR code in the corner of every slide, and this is kind of a mixture of things. Firstly, for you to register, so if you wouldn't mind just doing that once during the lecture, just to let me know that you're here. We're keeping a track of kind of who comes to lectures, just to get an idea really of the engagement with the course. But also, please use it, and you can fill this in and fill as much information as you want. So use it to register. You can ask questions when you register, or you can actually just do it anonymously and write questions. I've adjusted it slightly. It now says, you know, what's good, what's bad. So feel free to say, again, I noticed a few people said too fast. Please keep feeding that back. You know, if enough people feel we're going too fast, I'll try to slow down. Obviously within the bounds of what we need to cover for the course. Yeah. Okay, so this is an overview of the feedback we got. We got about 19 people feeding back, and this is kind of a word cloud. So what this shows you essentially is the size of the word is proportional to how many people had that word. So probably the biggest word is mostly. I'm not sure what that means, but really the key kind of interest of a lot of people here are MATLAB and programming, and getting a background in that. So that's good because essentially that's what we'll do. We've also got FEA there, which is unsurprising, and then understanding, analysis here, and then essentially simulation and application. So hopefully, at least within the kind of bounds of what we talk about, this should all be covered. And you've done some MATLAB courses. What I'm going to try and do is show you a little bit of MATLAB today, just to sort of ease you in. Next week we'll start to include more, and then gradually we'll ramp up, ready to start the hands-on tutorial, hopefully with enough background to kind of make progress. Yeah, there's one or two people said they're interested in ANSYS, which is kind of hidden in there. So within the applied exercise, there is some scope for you to be able to use your own methodology to validate what you're doing. So there is an opportunity to use ANSYS. I personally won't cover any ANSYS in this course, so I'm sorry if that's kind of what you expected from this course, but there won't be any explicit use of ANSYS, but you are welcome within the validation of the kind of MATLAB code you write to try to match it to ANSYS. So there will be an opportunity if you really want to explore that. But okay. And then again, there's just a few bits of comment and feedback. I've adjusted them slightly just to make them fit, but I think that the kind of enduring message is it depends on your background. If you're coming from 5 years working for industry, you're not going to remember the same things that people who are coming from straight from undergrad who've done this last year. So there's going to be a bit of kind of catch up for certain people who've forgotten concepts. Certain concepts maybe you won't know, and just please bear in mind if you don't understand something, it's because maybe you haven't got the kind of pieces in place to kind of be able to understand that. So you really need to kind of break apart the problem. Come and talk to me. I've set my office hours so they're actually after this lecture in 1:05. So feel free to come over if you're saying, look, I'm feeling like I'm missing these key skills. Then we can talk about sources to try and get better at those. And again, keep feeding back on the QR code. Just give me an idea if we're going too fast. And then it's just emphasising the difference in background. So we have a mixture of MEng and MSc. And my office hours are 4 o'clock today and 3 o'clock tomorrow. And I'm in 105 in Howell Building. There's also an opportunity on Blackboard to ask, rate, and read other people's questions. It's a bit like kind of Stack Overflow forum type sites. We could give that a go. If anyone wants to ask questions on there, then you're obviously welcome to email me directly, of course. But the advantage of that is then the questions are open, and you can read other people's questions, etc. So just check that out and see whether it's something that might work for this course. Okay, so the first couple of skills. solving simultaneous equations, and matrices and linear algebra. So thankfully no one said they haven't seen these before. We've at least got a background. Some people said they were maybe a bit rusty in these areas. So what we're going to do now is just a kind of short example that links these two concepts. The reason for doing this is the finite element method is essentially one of breaking the system up into a series of simultaneous equations, building them into a matrix and solving that. So this is kind of a fundamental skill in order to take on this course. So hopefully, everyone at least has a rough idea how to do that. So what I'm going to do is I'm going to show you, first of all, for the top equation, how we do that. And then, based on that, I'll give you a chance to try with the equations below. So 1 second. Okay. Here we go. It's okay, everyone can see? Right, perfect. So the idea really here is what we want to do is we want to take these simultaneous equations, make them into a matrix, and then solve that directly. So if you look at this, essentially what we want to do is we want to rewrite it in the form where we have some x and y matrix that we want to solve is equal to some right-hand side multiplied by some matrix of coefficients, where this matrix here we'll call K, this one we'll call U, and this one we'll call F. And the idea is once we've got these matrices, we can invert K, move it over to the other side and solve it. So it's essentially just a way of solving these simultaneous equations. So just to show you how we do this for this first equation here, the first thing we're going to do is rearrange it so that we've got basically in the right form to write it as K U equals F. So we're going to move the x component, 3x plus y is equal to 1. And we're going to move the x component over to the left-hand side on the second equation. So minus 2. So all we've done is just rearrange those by moving the x component to the left-hand side. And then essentially what we're going to do is we're going to rearrange it in a form where this matrix K here, we're going to rewrite in terms of the coefficients. So our coefficient for x is minus 3, and our coefficient for y here is 1. And similarly on the second equation, our coefficient for x is minus 1, and our coefficient for y is 2. So just to show you, basically with matrix algebra, the way it works is we multiply this term by this term, and we multiply this term here by this term here. So you can see if you do minus 3 times x, and then we do 1 times y, we get minus 3 plus 1, and that's all equal to the right-hand side, which is just 1 and minus 2. So you can see multiplying these through together, we get basically the first equation. And we do the same thing on the bottom row. So we do minus 1 times x, which gives us minus x. And we do 2 times y, which gives us 2y, and that's equal to minus 2. So essentially all we're doing is rewriting our matrix in that form. So this becomes K. So this is K, this is U, and this is F. And then all we do in order to solve for U is we do K to the minus 1 of F. So we're essentially rearranging our equation in order to solve that. So let me just show you on MATLAB how that would work. So with MATLAB, in order to derive the matrix K, we basically have a matrix here which is minus 3, 1, minus 1, 2. So the matrix K, we're going to do minus 3, 1, colon, minus 1, 2. Can you see that? It's a little bit far down. Let me see if I can move it up. So essentially this colon here just specifies that we want it as 2 separate columns. And then you can see what happens is MATLAB basically plots that. So we've got a minus 3, 1, minus 1, 2, as we have here. And then we're going to define the matrix F, which is just going to be equal to 1, minus 2, like that. And so then the process, in order to get for x and y, is we do K to the power of minus 1 times f. And that will give us the solution for x and y. So you can check that yourself and just make sure that it's consistent with what would happen if you solve the simultaneous equations directly. So if you take just 10-15 minutes just to convince yourself you're writing these two sets of equations as a matrix. So the first one is algebraic, which means you're doing the same process, rearranging it in the same way I just showed you, and then forming up a matrix on the left-hand side where you're solving for x and y each time. And then for the third one, we're solving for x, y, and z. So that's going to be a 3x3 matrix on the left-hand side, and an x, y, and z column on the right-hand side. Any questions at all? Stick your hand up or shout out, or I can come over to you and ask. We're about 10-15 minutes just for this. If anyone's completely lost, by the way, stick your hand up and I'll come and help. You've totally no idea what you're doing. way, if you finish this and you've also got MATLAB on a computer, feel free to try it out. I guess none of you got your laptop, have you? I was going to say, normally the typical way you do this is invert it by hand and solve it, but honestly I can't remember how to invert a matrix. It's been so long since I've done it because pretty much everything's numerical. So when it actually comes to solving these, you know, there's no reason to actually do it manually unless you're doing it algebraically or something. Okay, I'm going to show you how to do this, if that's okay. So the first one is exactly what we've just seen, but algebraic. So we essentially move, a to this side, and it becomes minus ax. Similarly with d, this becomes minus dx. So this essentially becomes a times the x component, and 1 times the y component. And then that's going to be equal to b. And then for the second term, we have minus d. Yeah, so this should be minus a. And then for this y component, we just have c, and that's going to be equal to minus e. So it's exactly what we saw before, just algebraically this time. Does that make sense? Anyone made any mistakes? Perfect. So okay, so for the next one, just to give you an idea of how these start to scale up, because essentially with finite element methodology, your elements can go to hundreds of thousands. So essentially you're solving these massive matrices. So we've seen it for 2 by 2, we're going to see it by 3 by 3, and then we're not doing any more by hand. But essentially the idea is to build up these matrices that you can then solve on a computer. So it's a way of solving many simultaneous equations. So with a 3 by 3 here, essentially what we want is a big matrix 3 by 3, which is going to be for the x, y, and z component. And then that's going to be equal to, and we can actually write the right hand side directly, just because this example is slightly easier. Okay, so the x component for the first one is 1, for the y and for z. So for the first equation, it's just 1 times x, 1 times y, 1 times z, and that gives us equal to 4. For the second equation, our first coefficient is 3 for the x component, minus 1 for the y component, and 6 for the z component. And then for the final equation, we have minus 4 for the x component. We have no y component, so that's just a 0. And then we have 2 for the z component. And again, we can just call this matrix K and U, and that's equal to F. So hopefully you can start to see how this becomes useful. You can get bigger and bigger system sizes, more and more simultaneous equations, and the process of solving them is exactly the same. I won't show you that on MATLAB just because it'll take me too long to type in. But essentially the process will be exactly the same. You build up a matrix of all of those coefficients. You do to the power of minus 1 to invert it, and you multiply the right hand side. Don't know if I wrote that explicitly, but your Ku is equal to F. You can rewrite as U is equal to K to the minus 1 of F. And the process there is we're essentially just multiplying both sides by minus 1, and these cancel. So it's just matrix algebra, but it has lots and lots of similarities with normal algebra, and you're doing it, there's kind of set rules, so you need to keep the order, which means the K has to still be on the left hand side, but otherwise, generally, for lots and lots of simultaneous equations, we can solve them with kind of quite concise notation. Okay, any questions? Is that okay? Perfect. Okay. So, vectors, tensors, and indices. I think this was something I was a little bit unfair in kind of rushing through lots and lots of this. As I said before, the main motivation is not because we'll cover too much of this in the course, just so you have a way of reading the literature, which is generally heavily mathematical. So I wanted to include just a kind of potted summary of that. But just to get an idea of the various notations out there, you can have vector notation, just one single underline, or double underline for matrix. Let's see if I can point on here. It's a little bit annoying. So yeah, does that work? Yeah. Okay. So that's for double underline for that, and then you just have the kind of bold notation for these various terms, and then there's this index notation, and the idea is the I and j will be replaced by say x and y, and then you get every permutation of those. Or you can do it numerically, where I and j just become x, so 1 or 2. So again, this is just what I said last time. I'll try to keep the notation simple and consistent, try to write all derivatives explicitly, and generally avoid index notation. I go back to some of those example equations again in this lecture. So I'm not expecting you to kind of understand all of the details of those, but just physically to understand what they actually describe and then how we kind of simplify those. But as always, any notational aspect, please just shout out or feel free to ask, and I'll update the notes. And again, this is all just because the literature is fairly impenetrable, I'd say, if you don't have this background. Okay, so just based on the plans for lectures, the idea is to recap last lecture, talk a bit about the shape functions or interpolation functions, talk again about differential equations, just state again what those are. I'm going to show you an example of weighted residual form. I'm not going to talk too much about that, I'm just going to use it, and then we'll go back and talk about the links with other forms. If we get time, we'll talk about local and global shape functions, but I think that's probably better next week. And then in terms of examples, we'll probably only do this first example here, and not the second example, but that's fine. Okay, so from the surveys, again, people fairly confident with calculus, with differential equations, which is good. So even if you're a beginner, hopefully we're not doing anything too complicated. And then the point is actually, once you know how to solve things with a finite element method, you don't have to know anything else about differential equations. Okay, so just to reiterate what I said last week, and this is kind of important just to understanding this methodology. This definition of a function. So I showed you all of those videos last week, computer games, Age of Ultron, various mathematical and computational simulations for engineering problems, fan blades, etc., etc. And the key underpinning concept of all of this was this idea of a function. That is, mathematically we describe the world using some function that models that evolves or changes according to some physical laws, and then from that we're trying to approximate that on a computer. But just be aware that the mathematical limiting case, this idea of a function, is actually the limit of infinite resolution, where you're talking about things as a continuum. So I mentioned this definition, I'm just going to mention it again, and it kind of underpins the majority of mathematics. So everything we talk about is based in continuum mechanics. This is a subset of continuum mechanics, and it all is based on this idea of a continuous function. That is one that, you can zoom in as far as you want. Now, in practice, we obviously can't, which is why we do the kind of numerical approximations, but we'll come back to that. Now, the key point about this continuum mechanics is it allows us to use the calculus. So I showed you this last week, this idea that you have some arbitrary function, whatever that may be, and you can get the gradient of it at any point by taking the difference between 2 points on that function, the point here minus the point here, separated by a distance delta x. And then the idea is that approximation is basically a straight line. Approximation to this kind of complicated function just within this kind of circle here, and then we gradually make that circle smaller and smaller and smaller. The smaller we make it, the better the approximation of a straight line is to a kind of continuous curve, and in the limiting case we end up with this concept of a derivative, which is basically the basis for differential equations. And then just be aware that essentially it's kind of a mathematical idealization, this limiting case where we can't ever really reach that limit, but it's essentially a placeholder that says mathematically this is what we'd like to do, and in practice what we're going to do is some approximation of that. Okay, so differential equations, and these equations, just any equation that includes a derivative is a differential equation, so hopefully it's not too intimidating a concept. Some very basic ones here. Remember I mentioned the kind of difference first order, second order, based on the highest order of the derivative, and then whether they're linear or non-linear. Not too important for this course, but just be aware of this when you come to solve them maybe later on in work, in how complex they are to solve, how many boundary conditions you need depend on the order and the complexity. In terms of differential equations, actually your common equations for a straight line and Newton's law are actually examples of differential equations where the gradient is just the derivative, and with Newton's law the acceleration is the second derivative with respect to time of the particle's position. Okay, so hopefully you've got an idea how you solve simple differential equations, and these are really, really simple. On the left-hand side, we've got a derivative, and the process is we basically integrate both sides. And in doing that, we get a function for x, where notice we have one arbitrary constant of integration. So a first order differential equation has one coefficient. And we'll come back to this, but this is also one boundary condition. And I'll explain what we mean about that later on today. For second order differential equations, this one you can solve by basically integrating twice. We integrate twice, we need two coefficients, two unknown coefficients essentially to solve those equations. And notice we also end up with basically a second order polynomial term. So we can say the solution of this differential equation is just a parabolic line. So we differentiated it twice. And when people talk about this, they say this is, one example of a general class of solutions, where the choice of C2 and C3 here will give you a specific solution, if that makes sense. And this comes back to this idea of boundary conditions. So physically, when we approximate a problem, the differential equation describes physically how the system will evolve, the physics of the problem. The boundary conditions then give you a specific example. And I'll talk about, basically physical interpretations of that. But with this, it's a very, very simple function. In practice, for finite element analysis, lots of the problems you solve are too complex that the function probably doesn't even exist at all. And even if it did, it'd be so complex to write, there wouldn't be much point in doing it. So actually, this approximation as a series of straight lines, as a series of elements, is probably an easier way to work anyway, even if we could do it a different way. So the important point to understand from all of this is the aim of FEA is to model the functions so we can actually use these differential equations. Okay, so these were the examples I talked about last time, and these are examples of differential equations. This is essentially just Newton's law. On the left-hand side, we have mass times acceleration. This is just the acceleration of a continuum, what's called particle, but it's essentially just a blob of stuff. So the evolution of that blob of stuff is equal to the divergence of the stress tensor. So that's the way the stress tensor changes. And you can think of this term essentially as being a force due to stress. So stress is basically just force if you take a slice through the substance, so that's all that's describing. And then body forces are things like gravity. So within this, we've got essentially Newton's law, and all of continuum mechanics is based on this equation, with some form of approximation for this stress tensor. And we gave loads of examples before with cars crashing and simple material tests here on the left, and then with a blade shearing off in a turbine. We also have the Navier Stokes equation. Now this is essentially Newton's law again. The difference here is it's in a different reference frame. So instead of following a blob or particle of substance, what we're doing is we're actually sitting in a volume, and we're watching the flow of fluid through that volume. So what we have is essentially the left-hand side is the acceleration, if you like, of fluid flowing through a box. And then we have this term that's the kind of pressure gradient, it's the pumping in a pipe, if you like. And then this diffusive term that measures how the fluid spreads out. So again, this is a differential equation. It's describing one of the key engineering areas of physics that we'd like to solve. And it's all based on this idea of a continuum, based on this idea of derivatives. Now these are Maxwell's equations, and anything with electromagnetic designs, things like transmission of radio waves, design of motors will have some form of this. And I showed this electric motor design because this is actually quite nice. It's a coupling of, say, fluid for cooling, it's electromagnetics for the generation of torque, for example. You could build in solid models, so it's kind of very multi-physics type of model. But when you come to solve this on ANSYS, you just click some buttons. But here we're kind of understanding these are the equations that you're discretizing and solving behind the scenes. And then finally, the heat flux equation. And this describes energy conservation. So it's just a statement that energy is conserved, which is just a statement that the change in energy in time is equal to the flow of energy, the advection, that's how much energy is carried by the flow. The stress work, so this is the energy that the flow does in being stretched and deformed, and how much it heats up due to viscosity and other concepts. And then we have the heat flux, which is essentially conduction. And generally this is approximating using Fourier's law, which is just some coefficient times the temperature gradient. And then finally, just to finish with the equation we'll solve in the exercise. And this is essentially containing some of the interesting elements of each of these equations, and it will give you a chance to kind of really get to the bottom of the various choices in your discretization of this equation and have key kind of elements of that. Okay, so how do we solve these differential equations? Well, as I said before, the mathematical idealization of a differential equation is the kind of limiting case if we can define a continuum. In practice, computers store things as binary information, ones and zeros, like you've seen with MATLAB, arrays of data, numbers. And we have to build up those arrays of numbers and solve them on a computer in some way. So whatever we do, we're going to approximate our solution as a series of points, a grid, or a set of elements. So the entire process of solving on a computer is one of discretizing and then essentially approximating our solution. And this fits nicely within the science. I bet it's kind of pretentious quote in there. Okay, so coming back to our picture of this kind of limiting case of the derivative, essentially we zoom back out again, and what we're going to do is we're going to just approximate that derivative as a straight line. So we're no longer requiring this kind of limiting case. We're actually just going to say we're happy just approximating our equation as a series of straight lines. And that's really the underlying premise of the finite element method, or finite element analysis, depending on which book you read. So this is our next exercise, and this is what I showed you last week. Essentially, you want to take this function, u of x, and by the way, I switch notation quite a lot in this. I go between u, t, just to get you used to the idea that actually these differential equations, these functions, aren't necessarily interpreted as one thing. And what you see is a lot of these differential equations describe the flow of different things. The flow of energy is the same as the flow of fluid in many, many cases. So I'll go through the kind of various implications and understandings of the various terms when we get to that. But essentially we're approximating the function ux as a series of straight lines. So these are joined where they meet at these what are called nodes, these points here, here and here. And the value of x0, x1, x2 and x3 have the corresponding values u0, u1, u2 and u3. And we number the elements 0, 1 and 2. So we're fitting a series of straight lines to approximate our function as closely as possible. Okay, so just to give you a kind of intuitive example of this, I wanted to actually choose a particular function. And I kind of started to do this last week, where essentially we're taking an exact answer, which we know is a cubic polynomial. And what we're going to do is we're going to connect a series of approximating straight lines, where the straight lines are going to have the same value at the nodes as the cubic polynomial. So if you look at this polynomial, when you put in the value, say, of 1, 2 and 3, you'll get these values of u1, u2 and u3 for that. So essentially what we're doing, bear one second, sorry, this is just a notation here. Just to remind you, the element numbers, u1 is just u at x is equal to x1. Similarly, u2 is x at x equals x2. Bear one second. Yeah, okay. Now I'll come back to the solution of the cubic in a sec. So the other thing I wanted to just recap is what we did last week. So if you remember last week, we started with the equation for a straight line between 2 points. That is the u element equation, which is just mx plus c. And the idea is we basically formed 2 simultaneous equations. One for u1, where we put in the value of x1, and one for u2, where we put in the value of x2 here. And essentially what we want to do is rearrange that to get the expression for an element. So the process here, which there is a video online you can watch again if you can't remember this, and we also spent some time working through, is essentially one of just solving these 2 simultaneous equations. So we're rearranging to get m and c from the 2 known values, which is the values at the end of u1 and u2 of a straight line. And this is what's called the interpolation function. So this is the basis of approximating our kind of continuous cubic function as a straight line here. Does anyone want me to go through this again? Are you happy with this? Show of hands, who'd like me to go through this again? Now. Okay, so you're happy for me to move on. You can always check this online, but basically it's just solving these equations. We end up rearranging terms, just purely algebra, and we end up with an expression for our equation for a line. U of the element is equal to n1, which is just this function, and n2, which is just that function, and it's an approximation for our straight line. And then we had this property that the derivatives of this function essentially just give you 1 over x2 minus x1, and we use the notation h is equal to x2 minus x1. So h is just the height or width of an element. So the derivative of n1 is minus 1 over h, and the derivative of n2 is 1 over h. And then just to show you the kind of link on that, du element by dx is going to be equal to dn1 by dx u1 plus dn2 dx u2. So what we've essentially done is we've rewritten the entire x functional dependence of the element just in terms of these shape functions, which then means we can get an expression which is of the form u2 minus u1 over h, where these 2 terms are h and minus 1 over h. So we've just collected them together. Does that make sense? Okay. Okay, so just to kind of reassure you that this would actually work and give you an idea of how well it works, let's consider an example of the 0th element here. So the shape function here for n0 is x1 minus x over this, which we called h. We call this h as well. And then the n1 expression is x minus x0 here. So essentially what we want to do is let's try taking the point of 0.5. So what we're going to do is we're actually going to look at the value of the straight line 0.5, and we're going to look at the value of the cubic polynomial 0.5. So in order to do that, we could actually put in the value of 0.5 into the cubic polynomial. So it'd be 0.5 cubed there, 0.5 squared there, and 0.5 there. And it turns out if you work through this, you get something like about 2.9 something from doing that. So if you've got a calculator or you'd like to convince yourself of that, feel free. I'll show you in MATLAB how we do that in a sec. But essentially, putting the values directly into the cubic function gives you that. Now what we're going to look at is how good an approximation this straight line is at that particular point. So we look at the expression for u0 at 0.5 here, and that's equal to, now the first term u0 here we know is equal to 0 because our u0 value is set to 0 at the origin. So we can get rid of that first term, and then we're actually just looking at n1 at 0.5 times u1. Now n1 at 0.5, we're essentially putting a value of 0.5 into here, minus 0, over h, and h is just 1. So what we end up with is an expression that's basically 0.5 u1, and we know u1 is equal to 3.2, so that ends up being a value of 1.6. So looking at that, it looks like a pretty poor approximation. We've actually got a value of 1.6 from our straight line, and the cubic function, the correct answer, if you like, is 2.9. So a couple of things to take away from this. Firstly, when you use quite a kind of complex function, generally you'll need more and more lines to approximate it correctly, and only in the limiting case will you get exactly the right answer. So let me just show you with MATLAB that same example. So you did the MATLAB courses, right? Did you look into functions? You covered functions and defining? Perfect, okay, and plotting, I imagine. So this is just an example before. So what I've done is just define a function that defines the cubic polynomial that you've just seen. So just to give you an idea, if we type in cubic line of 0.5, that's 2.79, not 2.9. So essentially what we've done is basically specified the input function variable is x, and it just sticks in that value of x into each of those and returns the answer for f, which is 2.9 at that point. We also have an expression for the element here, which is essentially taking in the value of x, u1, u2, x1, and x2. So notice we have to specify each of the various individual components in MATLAB. And so essentially what we'd do here is we'd put in, say, the value of 0.5 that we had. U1 was 3.2. U2 was, sorry, very wrong, actually, U1 is 0, sorry. U2 is 3.2. X1 is 0. And that is 1. So just to show you, so this is x0 or x1 and u0, and then u1 and x1. So we're basically just putting in those values and looking, and we get a value of 1.6. So essentially that's, and I've done that for each of these three different elements. Notice you've actually got to specify each of these values, and we'll come back to local shape functions that actually make this slightly easier. But this example, if we plot it for each of the different points, we end up showing the approximation. So you can see essentially why it's such a poor approximation looking at this. There's a very big gap between those two at 0.5. However, if we did 1.5, for example, actually the two agree very well. So what you'll find is different points, the approximation works better or worse. What I'll do is I'll upload these MATLAB scripts as well online, so you can play around with this and just get a kind of idea intuitively of how this works. Does that make sense? Any questions? Okay. Okay, and then this was the second line example, but I won't go through that. Okay, so the idea now is we're going to solve this differential equation. And And this is just a second order differential equation equal to 0, with boundary conditions of t equals 0 at x equals 0, and t equals 60 at x equals 0.3. So that's the example we're going to do. So essentially this, what I'd like you to do is just basically to solve that. When I mean say solve that, I mean integrate it twice and put in the boundary conditions. So essentially get the analytical solution of that differential equation. Now, one thing to be aware of when I mentioned before, the boundary conditions here, physically you can think of boundary conditions, and we'll come back to this in a sec, but these boundary conditions, if we're modelling a rod, this would be x equals 0, and this would say at 0.3, and what we're saying is the temperature here is equal to 60, and the temperature here is equal to 0. So these are called boundary conditions because physically they correspond to like places in space and the boundaries, the values at the end. But in terms of your actual solution of a differential equation, these are exactly the same thing that you use to get the unknown coefficients or the range of integration. So yeah, I'll give you maybe just over 5 minutes to do that. How are we doing for time? We'll do 5 minutes on that. I'll just talk through then the implications of that, and then we'll have a break afterwards. So I think last time I gave you an exercise during the break, and then no one took a break. So I think it's important to get up and have like maybe 10 minutes just to relax. Okay, is everyone happy with that? Still a couple minutes. let me just talk you through this solution. So essentially we just integrate twice. So the first integral gives you dt dx is equal to a constant 1. And then the second integral just gives you t as a function of x is equal to constant 1 times x plus constant 2. So we essentially have now this function t of x and two unknown coefficients. And this is where the boundary conditions come in. So we can first of all put in t at 0, which we know is equal to 0. And that's equal to c1 times 0 plus c2. So this just disappears. So now we know that c2 is equal to 0. C2 is equal to 0. And then we also put in the second boundary condition, so that's t of 0.3. So that's going to be equal to 60 degrees. And that's equal to c1 times 0.3. So we can basically rearrange to get c1 is equal to 60 over 0.3, which is basically 200. So the final equation we have, if we plot it, it's actually just a straight line between, this is 0.3 here, and t of x is basically equal to 200x. And this is 0, and this is t. Does that make sense? Everyone happy with that? So essentially it's just basically a process of integrating and solving this differential equation and putting in the boundary condition. Yeah. Okay, so then just to give you a kind of bit of context of why this is interesting. Well, let's take this Newton's law for continuum solid, and let's assume that it's not accelerating. That is, it's fixed in space, so this term's equal to 0. We assume it's got no body forces on it. Let's say, there's no gravity, there's no overall force acting on it. If we consider, say, a blob, and what we do is we actually apply some shear to it at the top. So you can think of this like a stack of cards, or maybe a bit of rubber that you're kind of stretching, or a test piece that you're applying under shear. What we would essentially see is the process of it shearing like this. And what we can essentially see from this is the stress equations we can actually approximate as some coefficient times strain rate, which would say be dr by dx. So essentially this divergence here of stress we can actually rewrite as mu d2r by dx squared is equal to 0. So essentially this model we've just shown you, which gives you a straight line, is basically the solution of an equation that essentially models, say, a test piece under shear, where the actual deformation of that test piece would essentially be described by a straight line, if you like. And this was the straight line we just saw before. So although it's a simple one-dimensional example, that's certainly one physical interpretation of that. From Navier-Stokes equation, we can do the same thing. Let's say we're going to look at a steady state. There's no change in time. We're going to look at laminar flow, so low Reynolds number. Essentially, the convective term we can say is negligible. And we're going to assume there's no pressure gradient. There's no pumping. Again, don't worry too much about these kind of various things. I just want you to understand essentially that this process of kind of simplifying these kind of complex equations, you can get these kind of minimal equations from that. Now, if we do this in one dimensions, what we have is viscosity times d2u by dx squared equals 0. And again, you can see this is an equation that gives you a straight line. Now, this is what's called coep flow. It's essentially between two channels where we've got a sliding top channel, fixed bottom channel, and we have essentially a linear velocity profile. So again, it's an interesting solution. And this would be an example, for example, say for any gap between two substances. So say you've got a car, a really badly drawn car. The gap here between the surface and the road could be modelled using coep flow. So let's say you were kind of doing some sort of large-scale analysis. Actually, it might be simple enough to use a one-dimensional model, just to look at the kind of drag underneath the car, for example. Or if you're modelling, say, a bearing, the actual gap between the bearing, potentially you could model using this coep flow. And lots of people essentially simulate many cases using this model. Finally, this example where, let's say you've got no stress working term, no advection, and no unsteady term. The simple case where all we have is conductive heat flow. We can approximate conductive heat flow using Fourier's law that we mentioned before. And again, you can see this is basically just minus k d2t by, in our case, dx squared. And then physically, you can think of this as basically being, if we had a flame on one end and we had, like, say, an ice cube on the other end, and we're modelling just the kind of heat flow through a beam. You can see this is the case we've just looked at, where T is equal to 0 at one end and T is equal to 60 at the other end. So again, this is a model, say, for heat flow, where you have very, very simple conduction through the substance. And then finally, you can see essentially the term we're interested in is this. For K is equal to a constant, if we assume this was constant, then we can actually just rewrite this term as K d2u by dx squared. So the example we'll get to by the end of our exercise is actually going to be a more complicated version of this, where we essentially are going to build in more and more terms. But just so you understand, what we've essentially solved there is that kind of very, very simple case. Okay, so just give you a maybe 5-10 minute break, and then what we'll do is we'll start to look at the finite element solution of that equation. So it's the simplest possible case. It's basically a straight line. We're now going to look at how you solve that with finite elements, but hopefully you appreciate it's actually a model for a range of complex physics. If we understand this, we can actually understand the general process. And any questions, feel free to stick your hand up or come down or whatever. Yeah, sure.
I have to scan the code.
Yes.
Scan code, so how can you? I'm really just about to.
Oh, I see. So I mean, on my phone at least,
Okay.
I mean, just using the camera recognises it. You may need a specific app. Try to switch your camera. A lot of cameras have
We need this one.
Yes, that's it. And then it's just an
For more class.
Uses el término encuentro caliente. Y